Hi, I'm Dhruvesh. I'm a PhD student at UMass Amherst, and I will be presenting our work on using pre-trained language models for visual planning. This is a joint work with Reality Labs and Meta AI. Imagine assembling a new piece of furniture or following a new recipe for a dinner party. For such tasks, you might follow a manual, going back and forth as you perform the steps. Now, instead of fumbling through the manual, imagine an assistive agent capable of visually tracking your progress and providing you with the upcoming steps as you perform the tasks. In this work, we take a step towards building such an agent. We introduce the task of visual planning for assistants, where given a natural language goal like building a shelf and an untrimmed video history depicting the visual history, the model needs to output the subsequent steps required to achieve the goal. We also introduce a novel approach for solving the task of visual planning, called Visual LM Planner or VLAMP. Our approach consists of two stages called segmentation and forecasting. In the first stage, the untrimmed video history is divided into action segments using a video action segmentation model. The segments from the history along with the goal are then passed through a multimodal sequence model, which uses a pre-trained language model. The sequence model outputs the subsequent actions required to achieve the goal. We discuss our modeling framework and both the modules in detail in the paper. We also introduce several baselines for the task of visual planning. These include heuristic baselines, baselines created by adapting models from procedural planning and long-term action anticipation literature, as well as purely prompt-based baselines like the ones that use GPT-3. Together, these baselines span several modeling paradigms. The heuristic baselines demonstrate the difficulty of the task, and we find that VLAMP outperforms all the baselines with large margins. We also perform extensive ablations and analysis that reveal several interesting observations. Following are just a few of these. We find that action and visual history improve complementary metrics. Specifically, while visual history improves the prediction of immediate next action, action history helps more with the actions that follow after that. Also, as one might expect, video action segmentation errors are detrimental to the performance. However, we find that availability of the visual observation history reduces its impact on the final performance. Another surprising fact we observe is that the errors do not drop as more history becomes available. We discuss these and a few more observations in detail in the paper. Thank you for listening. Please check out our webpage for the code and model checkpoints.